Well, hello, ladies and gentlemen. So today we're going to continue on with continue on with application of psychometrics, and we're going to shift to actual heating, ventilation, and air conditioning applications. So we're going to look at some sort of an air conditioning device, a humidifier, a dehumidifier, a heater, a cooler, some kind of application of psychometrics involving something that actually conditions the air in a building or in a house. We're going to apply the various energy and mass balances to solve the problem. And then we're going to finish up today by looking in general at HVAC processes. We'll talk a little bit about human comfort, what temperature and humidity, relative humidity ranges human beings tend to prefer. We're going to talk about how relative and absolute humidity depend on the air conditioning process. So we'll finish off the section on psychometrics by looking at general heating, ventilation, HVAC processes. But first, we're going to start off with a nice example, fairly detailed example involving a air conditioning process or heating, ventilation, and air conditioning. So what we have here is a two-part device. We have a duct, which contains an electric heater. So you see there we have some wires or a heating coil, and these wires are getting hot due to the dissipation of electric work or power, resulting in a heat rejection into a duct through which moist air is flowing from left to right. Moist air is flowing from left to right. Now, at the inlet of this duct, we have air coming in at 15 degrees C. The wet bulb has been determined, and the wet bulb temperature is 11 degrees C. The volume flow rate is 2 cubic meters per minute of moist air flowing into the duct. And then what happens is, of course, we heat up the air because we're adding heat by the electric work to the moist air flowing in. And then once we've heated up the air, we add H2O to it. We humidify the now warm moist air. We're raising the absolute humidity of the air by injecting H2O. So we have a little sprayer here. You can see that we're spraying little droplets of water into the duct, and that's vaporizing and increasing the vapor content of H2O in the air. The outlet temperature then, the temperature just before we get to the humidification here with the injection of H2O, the temperature right here after the heating at location 2 is measured at 20 degrees C. Then we add H2O, It can be a liquid, it could be a vapor, it could be anything. Maybe we're injecting steam here, I don't know. Who knows? Temperature at the outlet of this duct is 25 degrees C and a relative humidity of 65%. Notice that the temperatures here, T2 is 20 degrees and T3 is 25. This is probably an injection of some kind of vapor. Maybe it's steam. Maybe we're adding a little bit of steam. So if you like, I'm going to put right up here just to satisfy your curiosity. This is probably some kind of steam up here. It's probably not a liquid. It could be hot water. Maybe it's a hot liquid. It could be steam. Who knows? But the point is, temperature goes up from location 2 to location 3, probably because we're injecting either hot water or steam in the humidification part of the duct. So I want to point out here, in this part of the duct, we have simple heating. We're not injecting any H2O in this part of the duct. So we have what's called simple heating. All we're doing is heating the moist air in this part of the duct. And then in this part of the duct, we're adding moisture. So this is humidification. Humidification, we're increasing the humidity of the moist air by adding H2O in some form to the moist air, okay? So what are we supposed to find here? We're supposed to find the relative humidity at the inlet from the temperature, the dry bulb temperature, and the wet bulb temperature. I want to find the m dot, the mass flow rate for the dry air component going into the duct. Remember, it's moist air going in. The moist air is primarily composed of dry air plus a little bit of H2O vapor. So I want to find the m dot dry air that flows in and flows out of the duct. Then I want to find the heat transfer rate, Q dot in. What's the heat transfer rate in the simple heating section of the duct? Or air conditioning duct, if you like. And then I want to find out the mass flow rate for the H2O here. I want to find out the mass flow rate for the H2O. All right, so let's get started here. Let's get started. We're going to use a psychometric chart to do all this stuff. So life should be a lot easier than if you were trying to use saturation tables and equations relating absolute and relative humidity. It would be a lot harder. So, okay, so analysis. Okay, so let's find the relative humidity at the inlet. So the relative humidity at the inlet is equal to the relative humidity evaluated for some dry bulb temperature. Let's see, my dry bulb temperature is 15 degrees C. My dry bulb temperature is 15 degrees C and my wet bulb temperature is 11 degrees C. Maybe I had a hygrometer placed in the airstream and I am therefore allowed to get the wet bulb temperature and the dry bulb temperature. So T wet bulb is 11 degrees C. Okay, let's go to the psychometric chart and figure out what our inlet state is. Let's go to the psychometric chart here. Okay, so here's our psychometric chart. Let me find the dry bulb temperature first, T1. Let's see, we're at 15 degrees C. So T dry bulb at location 1 is 15 degrees C. Okay, so there's 15. And the wet bulb temperature is 11 degrees. So wet bulb temperature is right here. Wet bulb temperature is right here. Here's 10, here's 15, here's 20. So I guess 11, let's see, 10, 11, 12, 13, 14, 15. So 11 degrees is along this line right here. So T wet bulb 1 is 11 degrees C, and where they intersect, what's my relative humidity here? Let's see, let's go up. 60%. So relative humidity at location 1 is 60%. 60%, okay? So relative humidity is 60%. That's from the psychometric chart. 60%, and that's from the psychometric chart. Okay, so let me write that down here. So I've got relative humidity is 60%. Okay. Sorry, just writing this up and boxing it. Okay. Okay, now let's calculate 60%. Now let's calculate m dot for the dry air at the inlet. By the way, we're going to prove this in a minute. Well, maybe I don't even need to prove it. Notice there's no dry air injection anywhere. The only places where dry air is flowing in or out is the inlet at location 1 and the outlet at location 3. So when you do the mass balance on the dry air component, you'll find that m dot 1 is equal to m dot 2 is equal to m dot 3 and is all equal to the same m dot. So the dry air flow rate at the inlet, location 1, is going to end up being the dry air flow rate everywhere. But we'll see that in a minute. Okay, so let's calculate m dot for the dry air. Well, I do have the volume flow rate. Let's see here. So notice in general, m dot is equal to a volume flow rate, v dot, divided by a specific volume. Divided by a specific volume. Specific volume is cubic meters per kilogram. So the cubic meters per the volume per second divided by volume per mass gives you kilograms per second or kilograms per unit time. Okay, so I'm gonna look only, I want the dry air component. So I only want the dry air, and I want this at the inlet. So this is dry air at location 1. And that means I want the volume flow rate at the inlet, and this is volume flow rate for the mixture. So remember, this is for the mix. Cubic meters of mixture per unit time. And this here, if I make this a V tilde, this will be cubic meters per kilogram of dry air. So this is going to be cubic meters per unit time. And this is going to be cubic meters per kilogram of dry air. The cubic meters will cancel out, and I'll get kilograms of dry air per unit time. So V dot at the inlet divided by V tilde. I need to make sure I write V tilde at the inlet. V tilde at the inlet. So this will have units of cubic meters per kilogram of dry air. Okay, and that should give me m dot dry air. Let's see here. I have V dot. V dot is 2 cubic meters per minute. Probably need to convert that into seconds. 2 cubic meters per minute. Okay. So I have 2 cubic meters per minute. I think I'm gonna have to convert that into seconds. So 1 minute is 60 seconds. The minutes cancel out and I'll get cubic meters per second when I'm done. Okay, I need the specific volume of my inlet mixture per kilogram of dry air. So specific volume V tilde 1 is V tilde evaluated at 15 and 11 degrees C. So T dry bulb equals 15 degrees C and T wet bulb is 11 degrees C. Okay, let's see if I can find a specific volume here. Let's see if I can find a specific volume. Let's see here. Yes. Okay, so this is my state. So I'm looking for specific volume. Lines of specific volume. Here's 0.8, here's 0.85, here's 0.9. 0.81, 0.82. Looks to me like I'm halfway between 0.82 and 0.83. So how about 0. Let's just do 0.82. It's fairly close to 0.82. Let's just do that. So I'm going to write here. So 1, 2. So very close. So specific volume 1, approximately equal 0.82. If you want to do a 0.822 or a 23 there, that's fine. I don't think we need to be horribly accurate here. Okay, it's just kind of eyeballing it. 0.82. Very close. .82, and that's going to be cubic meters per kilogram dry air. 0.82 cubic meters per kilogram of dry air. Well, the cubic meters canceled out, and I get kilograms of dry air per second. Kilograms of dry air per second. So my m dot dry air is 0.041 kilograms of dry air per second. 0.41 kilograms of dry air per second. Kilograms of dry air per second. If you want to write that in terms of kilograms per minute, that's fine. That's just fine, okay? All right, so let's write that up here. Let's write that up here. So we have m dot dry air at the inlet is 0.041 kilograms of dry air per second. Kilograms of dry air per second, okay? 0.041. Okay. Okay, what are we supposed to do next here? We are supposed to calculate, let's calculate the heat transfer, Qin. Let's calculate the heat transfer. That is in the heating section, the simple heating section. Let me draw my control volume. By the way, I'm not going to include the wires. I'm going to exclude the wires. Why? Because if I include the wires, it'll be a work interaction, W dot electric. W dot electric is equal to Q dot electric, Q dot from the electric coils. But I want to immediately go to the heat transfer rate. So I'm going to exclude the wires, and this becomes a heat interaction instead of a work interaction. If I included the wires in my control volume, it would be a work interaction. But I'm going to exclude the wires, so it's going to be a heat interaction instead. It's going to be a heat interaction instead. Okay, so let's proceed. Let's proceed. So let's apply the energy balance for the heating section. Just for the heating section from state 1 to state 2. We're going to have to apply some mass balances too, but we'll do that in a minute. Let's see here. Q dot minus W dot is equal to dECV dt plus the sum of m dot H plus PE plus KE summed over all outlets minus the same thing summed over all inlets, okay? Now, we got a heat interaction going on here. We got a single inlet, a single outlet. Inlet is at location 1, outlet is at location 2. No work interaction because I've excluded the wire. It's a heat interaction. Let's assume it's steady state as well. Let's also neglect changes in kinetic and potential energy of the flow. Oh boy, I guess I got some assumptions here. So let's see, steady state. PE and KE terms are 0, so I'm going to neglect those. So the energy balance collapses down into something pretty simple. Let's see here. This is my Q dot in. No work. Steady state. No changes in kinetic and potential energy. And so I get Q dot in is equal to m dot H at the outlet, The outlet for my simple heating section. The outlet for my simple heating section is location 2, and the inlet is location 1. So I'm only looking at the heating section, not the humidification section. I have a temperature here. I have a temperature here. Okay, so this is m dot H2 minus m dot H1. Now, by the way, we haven't been, well, what have we been using so far on these problems? We haven't been using H, we've been using H tilde. So let me rewrite this in terms of m dot dry air. So m dot dry air, outlet minus inlet, okay? Outlet minus inlet. There we go, okay. Well, first of all, what's m dot for the dry air at location 1 and 2? I already know it for location 1. I know this. How about for location 2? How about for location 2? Let's do a dry air balance on the heating section. Dry air balance. Just on the heating section, okay? Just on the heating section. So we have the change of mass of dry air in my heating section control volume, CV, control volume, CV. dt is equal to the sum of the inlet dry air minus the outlet dry air. Okay? Steady state, so there's no change in dry air in my heating duct. I have one inlet. Let's see the inlet and the outlet for the dry air component in my moist air for the heating section. The inlet is at location 1, the outlet is at location 2. Okay. So this is m dot dA1, and this is m dot dA2. And so I get 0 equals m dot dA1 minus m dot dA2, or if you like, m dot dry air is the same everywhere. So m dot dry air is equal to m dot dry air 1, which is equal to m dot dry air 2. So all these m dot dry airs are the same. Okay, so I get, let me factor out the m dot dry air. And then I have H tilde out minus H tilde in. Okay? I already have the m dot dry air, check, so I'm in good shape. I'm in good shape on that. I can get H tilde 1, that's pretty easy to do. I can get H tilde 1, let's see here. H tilde 1 is equal to H tilde evaluated at a dry bulb temperature of 15 degrees C and a wet bulb temperature of 11 degrees C. So I go to the psychometric chart. Let's see if we can eyeball that one. 15 and 11. Let's go to the psychometric chart. So here is my state. And now, let me put, so there's my state. Again, hard to see. There's my state. Now, let's see, that says 30, 31, 32. Down here, not quite, not quite. Hard to see here. 31, 32, that's 32 down there. And that's 30, It looks to me like it's right around 30. Right around 30, maybe 31. So H tilde 1 is about 31 kilojoules per kilogram of dry air. About 31 kilojoules per kilogram of dry air. That's 30, that's 31, 30, 31. It looks like it's around 31, okay? Kilojoules per kilogram. Kilojoules per kilogram. 31 kilojoules per kilogram. And that's kilogram of dry air, okay? Dry air. So I got H tilde 1. Almost there. I just need to get H tilde 2. Well, H tilde 2, I need two properties. I know, what do I know about state 2? Not much. Not much. State 2 or location 2. All I know is the temperature of the air. I need one more property. One more property, and then I can locate the state on the psychometric chart. So I do know that the dry bulb temperature is T2, and that's 20 degrees C. I need something else. I need a relative humidity. I need an absolute humidity ratio. I need something. I need something to get a second property so I can find the state, okay? How about we try, if I can get a humidity ratio here. Let's see if I can get a humidity ratio. In fact, let's think about this for a minute. In the simple cooling section, m dot dry air is equal to m dot dry air out. N equals out, because we're not injecting any dry air. We're also not injecting any H2O in the simple heating section. So m dot H2O in is equal to m dot H2O out. And if you apply the mass balance for H2O, that's what you'll get. So if I go over here and I apply the mass balance, I'm not going to write it all out. But if we do a H2O balance on the heating section, so H2O balance on the heating section, what we're going to get is m dot H2O at location 1 is equal to m dot H2O at location 2. In fact, I'm going to move this over. So we're going to get a bunch of stuff, and then I'm going to get m dot H2O at location 1 is equal to m dot H2O at location 2, because we're not injecting any H2O into the simple heating section. That comes in the humidifier. The humidifier, the second section, is where we're injecting H2O, okay? Now let me divide our m dots there by m dot dry air. M dot dry air is the same as the inlet and the outlet. So let's just divide this by m dot dry air. So this is really m dot dry air 1, and that's m dot dry air 2. So this is actually m dot dry air 1 and m dot dry air 2, because the m dot dry air is the same in and out. Well, what is this quantity? M dot H2O over m dot dry air. M dot H2O over m dot dry air at the inlet and the outlet. That is the humidity ratio. So this is omega 1, and this is omega 2. So we get omega 1 is equal to omega 2. Okay, or maybe a better way of writing this, omega 2 is equal to omega 1. How about that? So omega 2 is equal to omega 1. And what is omega 1? Omega 1 is omega evaluated at the dry bulb temperature of 15 degrees C and a wet bulb temperature of 11 degrees C. Let's see if we can find the humidity ratio at the inlet. Let's see if we can find the humidity ratio at the inlet. Let's go back to the psychrometric chart. Okay, so we know our inlet state. There's our inlet state right there. Make sure I am horizontal, sorry about that. Looks to me like the humidity ratio, omega 1 at the inlet, is about 0.0064. And that'll have units of kilograms of H2O per kilogram of dry air, 0.0064. Let me write that up on the board. Getting a little cluttered here, so I'm going to get rid of this. .0064. Wait, make sure I don't have too many O's there. Yeah, 64 kilograms of H2O. Oh boy, running out of space here. Equals omega evaluated at 15 degrees C and T wet bulb 11 degrees C, 0.0064 kilograms of H2O per kilogram of dry air. Okay? So that's omega, Okay, so omega 2 is equal to omega 1, 0.0064. I'm not going to put the unit there. Kilograms of H2O per kilogram of dry air. Let's see if we can find the, let's see if we can find H2 tilde. Let's see here, H2. Here's H2. I'm sorry, T2. T2, dry bulb temperature is 20 degrees C. There's my dry bulb temperature, 20 degrees C, T2. That's at the heating section exit. Omega is the same. So now I'm going to try and get an H2 tilde. Looks like something a little bit over 35, maybe 36, could be 37. I'm going to write here H tilde 2 approximately equal 36 kilojoules per kilogram dry air. It might be 37. 36 is pretty darn close. 36 is pretty darn close, okay? 36 kilojoules per kilogram of dry air. Check, all done. All right, m dot dry air, what was it? 0.041 kilograms per second, 0.041, and that's kilograms of dry air per second. Make sure you keep the unit dry air, not moist air, dry air. And then I have H2 tilde, which is 36. H1 tilde is 31, and that has units of kilojoule per kilogram of dry air. Notice the dry airs cancel out and I get kilojoules per second or kilowatts, and I end up with, what do I end up with Q dot here? Q dot is 0.2 kilowatts. 0.2 kilowatts, or if you like, 200 watts. 200 watts, okay? So Q dot added in the heating section. Q dot in equals 0.2 kilowatts. .2 kilowatts, okay? That's in the heating section. That's in the heating section. Okay, what are we supposed to calculate last? We're supposed to calculate the mass flow rate injected in the sprayer, by the sprayer in this humidification section. So now we're going from location 2 to 3. I don't know anything about any heat addition. I don't even know what the temperature of this H2O is. The point is we're adding some H2O and it's resulting probably in a humidification, it should be, in a humidification of the air. The outlet temperature, dry bulb temperature, and relative humidity are given. So now I need to calculate what m dot is for the H2O. Okay, so let's go back and now we're going to apply a mass balance for the H2O. Let's apply a mass balance for the H2O on the humidification section. Let's apply a mass balance just for the H2O component in our moist air in the humidification section. So H2O mass balance, and that's for the humidification section. Humidification section. Just for the humidification section, not the heating section. Just for the humidification section. Okay, so let's write out the mass balance. dm of H2O within my control volume, which is my, I got to define the control volume. So my humidifier is going to have an inlet at location 2 and an outlet at location 1. So this is going to be my control volume. Of course, we have m dot H2O occurring right here. So we'll have 2 inlets and 1 outlet. 2 inlets and 1 outlet. Let's see here. Time rate of change of H2O within my humidification section is equal to the sum of m dot in minus the sum of m dot, and this is H2O. M dot H2O in minus the sum of H2O out. Steady state. So this is 0. I have 2 inlets. I have an inlet at location 2 and the mass flow rate for the injected water. So I have an m dot H2O2 and I have an m dot H2O here. I haven't given this, I guess I'll call this location 4. So this is m dot H2O4. How about we'll just call it that. Got to call it something. So this is m dot H2O2 plus m dot H2O4. The outlet mass flow for the H2O, that occurs at location 3. The outlet, only single outlet, that occurs at location 3, so I have an m dot H2O3 for the outlet. Okay. Now what I want to find is m dot H2O at location 4, which is my m dot H2O. So I solve this and I get m dot H2O4 is equal to m dot H2O at the outlet, which is location 3, minus m dot H2O at the inlet, which is location 2. Okay? Now, how about I divide and multiply this by m dot dry air? The mass flow rate m dot dry air is the same everywhere. So this guy becomes m dot dry air times m dot H2O divided by m dot dry air at location 2 minus m dot H2O divided by m dot dry air at location 1. Okay, because the mass flow rate for the dry air is the same everywhere. So m dot, oh, I'm sorry, 3 and 2. So m dot dry air 2 is equal to m dot dry air 3, which is equal to m dot dry air. Okay, this is the humidity ratio at the outlet. So this is omega 3, and this is omega 2. So m dot H2O is equal to m dot for the dry air times omega 3 minus omega 2. Now I have m dot for the dry air. Check, I already calculated it. I also have omega at the inlet of the humidification section. So there it is, 0.006. 0.006. I've got that. I've got that. So now I need omega at the outlet, omega 3. I need omega at the outlet. Omega 3, that's going to be omega evaluated. What do I know about the outlet? I know a relative humidity and I know a temperature. 25 degrees C is 65%. Two properties, in theory, I should be able to get omega at the outlet. So temperature, T3, and that's a dry bulb temperature, 25 degrees C, and a relative humidity, 65%. I go to the psychrometric chart. Let's go to the psychrometric chart here. 25 and 65, 25 degrees for the dry bulb temperature, 65%. Let's see here. Here's 25 degrees. Kind of running out of space here. T3, 25 degrees C. That's a dry bulb temperature, the temperature. And then I have a relative humidity of 65%. Here's 60, here's 70. So it's right in between here somewhere. Like right there. Looks like it's going to be right around and right around 50, right around 60, maybe 59. So H tilde 3, about 59 kilojoules per kilogram of dry air, about 59, okay? I'm gonna put 59 in. All right, so H tilde 3, about 59. Oh, I'm sorry, what? I don't want H tilde 3, I want the humidity ratio. What am I doing? What am I doing? Share, there we go. Okay, all right. let's get back. So 20 degrees, our state is right here. So let me find my, that looks pretty good. Oops. Looks like about, so omega 3, about 0.013, maybe 5 kilograms H2O per kilogram dry air. So basically 0.0135, 0135. 0135. Close enough, close enough. About 0.0135, and that is kilograms of H2O per kilogram of dry air. Okay, check. Oh boy. All right. M dot for the dry air. Calculated that before. 0.041 kilograms of dry air per second. .041 kilograms dry air per second, and then I've got omega 3 minus omega 2. So I have 0.0135 minus 0.006, and that has units of kilograms of H2O per kilogram of dry air. Notice the kilograms of dry air cancel out, and I get kilograms per second of H2O. Kilogram per second of H2O. Let's crank this out. Let's crank this out. Let's see here, 0.0135 minus 0.006 times 0.041. I'm going to write this in terms of, it's a pretty small number. Let's do it per minute. I guess this is right. This is just fine. Let's see here. Oh boy. 1, 2, 3, 4. So 3 times 10 to the minus 4 kilograms per second of H2O. I think I'm going to rewrite that. Maybe let's do it per minute. Everything was in per minute. So let's multiply that by 60. So M dot H2O, and that's at location 4, 0.0003. I don't know what I'm trying to do here. 10 to the negative 4 kilograms of H2O per second. Let's get this on a per minute basis, or if you like, 0.01845 kilograms per minute. Let's see, there's 1,000 kilograms per cubic meter approximately for H2O if it's a liquid. So this is about 2/100ths of a liter per minute, 2/100ths of a liter per minute. So it's approximately 0.02 liters per minute in terms of volume flow rate. That's V dot H2O. Okay. It's not a mass flow rate, it's a V dot. Okay, so let's finish this up. This mass flow rate, so M dot H2O at location 4, it doesn't matter, 0.02 kilograms of H2O per minute, okay? 0.02 kilograms of H2O per minute. Okay, that's it. Okay, so let's take a break for a second. Okay, let's finish off here with a general review of heating, ventilation, and air conditioning processes that are possible and how that affects the humidity ratio and relative humidity. So what we have here is a device that includes most possible heating, ventilation, and air conditioning processes. We have moist air flowing in, moist air flowing out, and we can do some stuff to it. We can either add heat using some sort of heating coils. We can cool the mixture. So this would be an air conditioning process where we reduce the temperature and absorb heat. Maybe there's some refrigerant flowing through these coils here, some sort of refrigerant, so the coils are cold. As a result, the moisture condenses on the coils and liquid water drips down and is drained away. Let's say. So a possibility here is cooling, heating, and the cooling may contain dehumidification, where we drain away some of the condensate, the H2O condensate. And we can also have humidification going on by spraying H2O into the duct or the device. Okay, so there's all these possibilities. Let's make a little table here. Let's look at process. Let's talk about the relationship between absolute humidity, and let's talk about relative humidity as well, okay? So let's look at the simplest cases possible. Let's say we have simple heating. Simple heating. That would be the case where we have a heating coil and nothing else. No condensation, no cooling going on, no humidification going on, just simple heating. Simple heating. So in that case, if you do a mass balance on the air, the dry air, and the H2O for simple heating, no humidification, no dehumidification, no water being added, no water being extracted, simple heating, you get m dot dry air in is equal to m dot dry air out, m dot H2O in is equal to m dot H2O out, and therefore the absolute humidity or humidity ratio at the inlet is equal to that at the outlet. So we'll get omega in is equal to omega out. Simple heating. Now, if there's simple heating going on, that means temperature is going up from the inlet to the outlet. Temperature is going up. That means the saturation pressure is going up compared to the inlet. The saturation pressure is going up, but the partial pressure of the H2O is staying the same. That means the relative humidity is going down. So relative humidity at the inlet is greater than relative humidity at the outlet. Why is that? Because the saturation pressure for the H2O is the same in the inlet and the outlet. We're not adding any H2O, but the saturation pressure is going up because it's warmer. We're heating the air, so it's warmer at the outlet compared to the inlet. Okay? Now, what about simple cooling? That's where we're extracting heat, but we're not extracting any H2O. So simple cooling. Simple cooling. Well, again, we're not adding or subtracting any H2O. So omega in is equal to omega out. But now the air is colder at the outlet compared to the inlet. So the outlet relative humidity is higher than the inlet relative humidity. So the outlet relative humidity is greater than the inlet relative humidity. Okay? I think I need to say in and out. In, out, not 1 and 2. In, out. Okay? We can also do heating with humidification. Heating with humidification. Humidification. Heating with humidification. Gonna run out of room here soon. Heating with humidification. Heating with humidification. So that's where we're heating the air and then we're adding H2O. So clearly, the outlet humidity ratio is greater than the inlet humidity ratio because we're adding H2O. In terms of relative humidity, well, heating reduces relative humidity, but adding H2O increases relative humidity. So depending on how much H2O is being added and how much heating is being done, humidity could go up or down. So I don't know which way it's going to go, so I'm just going to put a dashed line right there. Now, what about heating? What about heating with dehumidification? So we have heating with dehumidification. So we're extracting H2O and then we're heating the air. We're drying the air out and then we're extracting H2O. One way you could do that is by having a cooling coil. Drain some of the H2O away once you've cooled the air and then reheat it. So you could either heat it and then cool it, or you could cool it, condense the H2O, and then heat it. In any case, omega at the inlet is greater than omega at the outlet. The humidity ratio goes down because we're extracting H2O from the flow. If we're heating it, that means relative humidity goes down. If we're extracting H2O, that also means relative humidity goes down. So I can definitely say that the inlet relative humidity is greater than the outlet relative humidity. Okay? And then we got, how about cooling? Cooling with humidification. Cooling with humidification, that would be where we cool, no heater, we cool the air, maybe, and then we add moisture to it. Maybe we don't cool it so much that it starts to condense, we cool it a bit, and then we add H2O. Who knows? Who knows? Actually, if you inject H2O liquid, you could use the change in enthalpy as the H2O evaporates to automatically cool the air. By the way, those are called swamp coolers. Swamp coolers are devices that inject moisture into relatively hot, dry air. They inject liquid H2O into hot, dry air, and the liquid H2O evaporates, chilling the air. So that's a swamp cooler. So that would be where you had heating, cooling with some sort of humidification going on, presumably. So in this case, omega in is less than omega out. Let's see here. If you cool the air, the relative humidity goes down. Goes up. If you cool the air, the relative humidity goes up because the vapor pressure goes down. And you're also adding H2O, so that pushes the relative humidity up even more. So I guess unambiguously, the inlet relative humidity would be less than the outlet relative humidity, okay? Because you're adding H2O and you're reducing temperature. Both those things are pushing up the relative humidity. And then finally, we have cooling with dehumidification. Dehumidification is where we extract H2O. Cooling is where we reduce the temperature or extract heat, let's say. Well, we could do that with some cooling coils where we siphon off or drain away the condensate that's condensing on the cooling coils. Clearly, the outlet, absolute humidity is less than the inlet absolute humidity or humidity ratio. That's going to reduce the relative humidity, but it's going to get cooler, so that's going to raise the relative humidity. So depending on the trade-off there, it's either going to raise or lower the relative humidity. So I don't know what the general trend is. It could raise or lower the relative humidity, okay? Now, for those of you that are going to get into HVAC applications, heating, ventilation, and air conditioning, human comfort. What's the range of temperature and relative humidity that is most important or most advantageous for human comfort? So let's finish off by discussing what some of the ranges are for temperature and relative humidity that people are fairly comfortable with. What are you going to encounter indoors in a workplace, in a shopping area, in a home? Okay, so human comfort. Human comfort. So typically here, I have some ranges here. I had some somewhere. Usually it's around 50%. Let's see, what do I say in the notes here? What do I say in the notes? It's around 50% relative humidity is considered comfortable for human beings. I don't know where I say it here, so I'll just say it again. So human comfort, typically relative humidity is typically 50%, let's say plus or minus 10%. That's what's considered comfortable for humans. And of course, temperature, something around room temperature. So temperature is 25 degrees C. Let's say plus or minus 2 degrees C. So that turns out to be around 70, 75, 68 to 75 degrees Fahrenheit, something like that, okay? That's considered pretty reasonable. All right, ladies and gentlemen, we've done quite a bit on psychometrics. We've extended this to heating, ventilation, and air conditioning. We spent the whole lecture on heating, ventilation, and air conditioning after working with basic psychometric concepts in the previous couple of lectures. So now we're going to move on to reacting systems, mixtures, fuel and air, or fuel and an oxidizer. We're going to move on to systems that actually react with each other. Fuel burns, reacting systems, chemical reactions, and we're going to learn how to treat these systems in a thermodynamic way. All right? So take care, ladies and gentlemen. Take care.